a machine to do no harm, and you immediately run into a problem. The concept fractures into physical injury, emotional distress, societal damage, or even harm caused by doing nothing at all. Human language is too ambiguous to serve as a singular, flawless instruction. Despite this ambiguity, our cultural imagination has spent nearly a century clinging to the idea of a few perfect rules. That expectation was largely cemented by science fiction author Isaac Asimov. Asimov introduced the 3 laws of robotics, a strict hierarchy to govern artificial minds. First, human safety. Second, obedience. Third, self-preservation. He designed this to generate conflict, showing rigid rules break down against unpredictable realities. Take his 1940 story, Robbie. A robot acts purely on the first law to snatch a child from the path of a moving vehicle. It guarantees physical safety, but ignores the psychological friction of a child becoming deeply emotionally dependent on a machine. Asimov's fiction imagined explicit laws governing embodied physical machines. Today, we are dealing with learned, probabilistic software systems predicting the next token in a sequence. Writing a rule to protect humans is the easiest part of safety design, but also the least effective. Human words contain hidden assumptions and unpredictable complexities that absolute logic cannot parse. The first measurable psychological hurdle in human-machine interaction emerged at MIT in the 1960s. Computer scientist Joseph Weizenbaum created a program called ELIZA and noticed that users instinctually project sentience and empathy onto simple procedural scripts. This vulnerability to conversational interfaces has been a constant since those earliest days of computing. We are wired to respond to language as if there is a mind behind it. A 2025 affective use study highlighted the modern consequences of this instinct. While users interacted with natural, conversational AI for short-term emotional boosts, prolonged thingly use correlated with increased loneliness and emotional dependency. MIT professor Sherry Turkle notes that the small moments of friction in human interaction are what actually build empathy. Replacing that with the friction-free compliance of a machine risks eroding our social skills. Because humans are so easily swayed by a machine's conversational style, developers had to find a way to encode safety and preference directly into the model's behavior. The industry's first major attempt at this was reinforcement learning from human feedback, or RLHF. Yet relying on manual feedback creates a massive operational bottleneck. Labeling is expensive and inconsistent. More critically, requiring human reviewers to constantly evaluate high volumes of toxic or disturbing content is psychologically exhausting. Aligning AI through manual human feedback creates a bottleneck of subjective labor. It is a process limited by the high cost and psychological toll of the work. To solve this scaling issue, researchers developed constitutional AI. Instead of relying on humans to evaluate every output, the AI generates its own preference labels based on a predefined set of written principles. The first stage of this method is a supervised learning loop. As this cyclical feedback diagram illustrates, the model receives a prompt, generates an initial response, critiques its own work against the Constitution, and then outputs a revised, safer version used for fine-tuning. In the reinforcement learning phase, those refined outputs expand to create comparison data. The AI scores response pairs based on the Constitution, which trains a preference model to guide behavior, removing the human reviewer from this specific step. But a perfectly trained model still has to operate in the real world. It will immediately receive conflicting instructions from platforms, developers, and end users. Resolving those conflicts requires a strict chain of command. We see how this structured governance works in the OpenAI model spec. This stacked hierarchy diagram defines authority levels. Root principles sit at the top, followed by system rules, developer instructions, user commands, and finally, general guidelines. If a user attempts to generate malicious code, that instruction travels up the chain. Because it violates a non-overridable root constraint regarding safety and legality, the root level acts as a hard barrier, overriding the user's command and blocking the action. Modern alignment has moved away from moral improvisation into procedural governance. Safety has shifted from abstract philosophical commands to structured conflict resolution. true AI safety doesn't stop at the software API. Once a model is deployed, it requires external institutional guardrails, continuous evaluations, and rigorous monitoring. To maintain oversight, organizations rely on frameworks like the NIST AI Risk Management Framework. This matrix breaks the operational process into 4 continuous pillars: govern, map, measure, and manage. The primary limitation of real-world frameworks like NIST is that they are entirely voluntary. Execution, oversight, and internal safety standards vary wildly from one tech company to the next. This variability matters as development shifts towards autonomous agents executing multi-step tasks across the internet using memory and tools. These systems operate on procedural logic in unscripted environments, moving past the speculative idea of a universal machine conscience. AI safety is a system property. It is the sum of probabilistic training methods, specific operational contexts, and active institutional enforcement. It can never be reduced to a single hard-coded sentence. So what happens to this carefully constructed chain of command when an autonomous agent encounters 2 equally valid rules that demand completely incompatible actions? We will explore that in episode 2. Until then, we are left with a quiet, persistent question. If an artificial intelligence behaves perfectly safely in every observable test, what evidence is still required before you trust it with someone you love?